This presentation is delivered by the Stanford Center for Professional Development.
Hey everyone, welcome. I have one handout for you today. It is assignment 3. It is due next Thursday evening. You'll get assignment 4 next Wednesday. It'll be due the following Thursday evening. You'll get a written problem set a few Wednesdays from now. It won't need to be turned in. I'll talk about that more when I actually give it out. But it'll provide a collection of written problems that you'll be responsible for the midterm come the following Wednesday night. When I left you on Monday, I had really just gotten through what at the moment was the full implementation over generic stack. I've actually made parts of it easier than it really needs to be because we focused on storing ints and doubles and characters and booleans. What I want to do now is put off the implementation for about 10 or 15 minutes, look at that again, and think about how we would use it to store a stack, use a generic stack right there to store a collection of strings and print them out in reverse order. Now the nonsense code I'm going to put on the board is effectively going to just print out the reverse of an array, but it's really in place to illustrate the mechanics of using those 4 functions when you're storing C strings. That's going to become very important come assignment 4 to manipulate C strings, so that's why I want to do this. So just imagine this right here being your main function. I don't care about argc and argv, but I do care about declaring one of these things. And I'll emphasize the fact that it is a string stack. And what I want to do is I want to press on 4 deep copies of these strings right here. Const char star, I'll just say letters, is equal to, actually, you know what, let me not call them letters. We'll just say friends. And I'll set it equal to this array. Al, Bob, Carl, and that'll be enough. So what I want to do is I want to declare one of these stacks. This picture I get right here, according to that type def over there, isn't very sophisticated. It's 16 bytes of nothing, or nothing meaningful. Okay, but I rely on stack new ampersand of string stack, where I pass in size of char star. And all of a sudden now it's getting a little complicated. I'm going to ask the stack to basically keep track of the addresses of dynamically allocated C strings. Okay? So what I want to do is I just got this picture. This points to a 16-byte blob. 4 bytes, there's no, the depth of the stack is 0, but I have space before elements. This 4 right here is really size of char star. What I want to do is I want a for loop from I is equal to 0, I less than 3, because I want to go ahead and I want to make a copy of each one of those strings. I do this. Char star, I'll call it copy, is equal to stirdup of friends of I. Okay. This is an important enough variable that I actually want to draw it. Copy. On the very first iteration, when I is equal to 0, it is set to point to a deep copy of al \0 in the heap. What I want to do, and I think this is the best way to phrase it, is that when you push an element onto the stack, you transfer ownership from mu to the stack. And the way you do that, based on this right here, is for me to do stack push which stack, this string stack that I've just initialized, there's some drama and controversy over what the next argument should be. Since I am storing car stars, that means that these things, even though the stack doesn't know it, that they have to hold as material these 4-byte character pointers. Okay? That means that I have to pass in the address of a car star so it knows to go to that address and copy the four bytes into the stack. Does that make sense to people? Okay. Because I'm putting the ampersand here, it knows to go and replicate that material right there so that it points there, increments this to a 1. On the very next iteration, I reuse and I actually destroy and redeclare copy to no longer point to Al, but as it's redeclared and reinitialized, it's set to point up to Bob. This is copy on the second iteration. I pass that in. It replicates the material that's in there because it has the address of that size of car star figure so that it can replicate that address right here. And so it's almost like this as a for loop blows up 3 balloons, okay, with Al, Bob, and Carl's name on it. And then knowingly mem copies the end of the string or the tail of the string and actually copies it to the stack behind the scenes. Do you understand what I mean when I say that? Okay, so I'm really transferring ownership of these 3 dynamically allocated copies over to the stack. What I want to do now is I want to go ahead and I want to print these things out. I really want to ask for ownership back. So I'm going to do this car star name and then for int I is equal to 0, I less than 3, I plus plus. What I want to do is I want to ask for the stack to pop off string stack, and I want it to place the most recently pressed or pushed kite string back into the space that's right here. Okay? So I want it to, this would have been set up to point to Carl. I want it to replicate this space in my local variable called name, so that this ends up pointing to Carl, and the logical length of the entire stack is decremented to 2. Okay? Does that make sense? The way I do that is like this. Then I can do this. This is the equivalent in C of cout. Printf, where this is the string, %s is a placeholder for the string to be printed. And then I can go ahead and free name. Okay, that means that it basically passes the end of the kite string or the end of the balloon string to the deallocator, so it goes to the Carl address or the Al address or the Bob address and actually donates that memory back to the heap. I want to be clean about it. I do stack dispose at the end, and I just pass in ampersand of string stack, and that is that. Okay. Now, these ampersands right here typically don't surprise people because I'm dealing with a direct allocation on the stack frame of this function, of a thing called string stack, and I have to pass the location of it around. Okay. These ampersands right there very often surprise people. If you did not put them there, for many of the same reasons we saw in previous examples, it would still compile and run. But if you provide this address to stack push, then you're getting it right. But if you actually don't include the ampersand right there and you pass in that value right there, it's going to go ahead and replicate bob \0 as if it's an address and copy that into the stack frame. Okay, that's not what you want. Okay, does that make sense? Okay, very good. Now the problem comes, suppose I go ahead and I comment all of this out. or I set this equal to I less than 2 or something. Suppose at the time I actually call stack dispose. The stack actually has some material that it still owns. Okay? I've been very symmetric in the way that I allocate, build up, bring down, and then dispose of. But the stack shouldn't be obligated to be empty, or the client shouldn't be forced to pop everything off the stack before they call stack dispose. Stack dispose should be able to say, okay, I seem to have retained ownership of some elements that were pressed onto me. I would like to be able to dispose of these things on behalf of the client before I go and clean up and donate this blob of memory back to the heap. Okay? Many times there's nothing to be done at all. When this thing stores ints or longs or doubles or characters, you don't have to go in and zero them out. That's really not that useful. You do have to be careful about donating back any dynamically allocated resources or maybe any open files. That's less common, but dynamic memory allocation is certainly more common. If these things really are owned by the stack at the time it's disposed of, then the stack dispose function has to figure out how to actually pass these things right there to free, just like we do right there. Does that make sense to people? Okay. It's actually very difficult to do that because the implementation of stack dispose doesn't actually know that these things are pointers. It just knows at best that they're 4-byte figures. It is capable of computing these addresses. And so if the depth of the stack is 3, so that those 3 arrows are arrows that point to elements it's holding for the client, it could pass those 3 arrows to some disposal function. Okay? Now, this isn't always going to be a simple pointer. This might be a struct with 3 pointers inside. Okay? It might be itself a pointer to a struct that has 3 pointers inside. So you want to have some very general framework for being able to free whatever's at those 3 arrows if, in fact, there's any freeing needs. So what I want to do here is I want to upgrade this right here to not take 2 arguments, but to take 3 arguments. And this is what it's going to look like. This is the upgraded stack new function. Stack new is going to do that. It's going to take an lem size. And it's also going to take this. Void free function takes a void star and doesn't return anything. The idea here is that I want to pass to the constructor function information about how to destroy any elements that it holds for me when I call stack dispose. Okay? Those 3 arrows, if you're dealing with a stack of depth 3 and it's storing strings, it's prepared to pass those 3 things in sequence. At least that's what I want to write code for. Those 3 things in sequence to this function that you write and pass the name of to your stack new function. Okay? And it will invoke this function for every single element it holds for you. Since we write this, we can accept the void stars right there, reinterpret them in this case to be the car star stars we know them to be, dereference them, and pass them to free. Okay? Does that make sense to people? Yes, no? Okay. So I have to rewrite a few things. I have to actually store the free function as a field inside the struct. That means that this is a picture. We'll actually have this 5th field that points to a block of code that knows how to free things for me. Okay? We have to also handle the scenario where we're storing ints or doubles in the stack, and there actually is no freeing to be done on behalf of those things. So the client, when they call this new function, they're supposed to pass in the first 2 arguments as they always have. If you're storing these base types that have no freeing needs, I expect the client to pass in a null here, and that will be checked for in stack dispose. If you're storing things like car stars or pointers to structs or even direct structs that have pointers inside that are pointed to dynamically allocated memory, then you'd have a meaningful free function placed right here. Okay? Does that make sense? Okay. So let me rewrite stack new. I'm sorry, not stack new. This is easy. Let me rewrite stack dispose. Stack asterisk S. Understand that now I'm getting the pointer of one of these 5 field structures, where the 5th field is actually either some null pointer or a pointer to a legitimate freeing function. Before I go ahead and dispose of the lens blob, I better check to see whether or not anything complicated is residing within the log length elements that are still inside. If it is the case that S arrow free function, that's the name I gave to that field up there. I don't want to be too clever when I do that, so let me say if it's not equal to null, then that means I have to apply this free function as a block of code against those 3 arrows, or all of the arrows that come up, the manual addresses, the manually computed addresses of all the things that reside behind the scenes. You could do this. For int I is equal to 0, I less than s, log length I plus plus. I would just do s arrow free function char star s arrow lems plus I times s arrow lem size. Okay, and I think people don't usually argue with that because it's something they've seen before, so they kind of trust it. It's not difficult to get that part right when you know you're storing a free function. Okay, the part that's difficult to get right is writing the free function itself. Let's revisit this example. Now that we know that when we store strings, we actually have to potentially set up the stack, or set up the stack to potentially delete elements for us. That means when we declare a stack called string stack, and we call stack new, with size of char star and I want to pass in some function called string free. I'm just contriving the name. I do know that it has to match that right there as a prototype. It has to take a void star and return nothing. I have the responsibility of actually writing the string free function. Well, I have to set up string free to actually accept a void star knowing that it's really a char star star. Does that make sense to people? Okay, just revisit this picture. These are the types of things that are going to be passed to my free function. I need to reinterpret that as something that's at least dereferenceable, okay? And then hop into the actual rectangle or the box and take that number and pass it to the free function, okay? So, as an aside, prior to doing this, you would implement string free to take a void star, whoops, let's give it a name, lem or VP or whatever you want to do. And because I'm writing this specifically for the char star stack case, I would just do this. This is really an asterisk. It just came out badly. Okay, that's a good asterisk. Okay, now what happens if I forget this and I forget that? Think about what actually gets passed to free. If I don't cast this to at least be a double pointer, and I'm actually casting it to be a char double pointer because I know it's really 2 hops away as an arrow to characters, and dereference, this dereference is really what matters. It's the thing that takes me from this little fence post right there to the box that's addressed by the fence post, okay? If I do leave that way, it will pass this address to free. It will pass that address to the free function. It will pass that address to the free function. And that's bad because the first one actually can be passed to free. You shouldn't be doing that though because you didn't allocate that block. These two addresses should certainly not be passed to free because they weren't directly handed back to anyone via a call to malloc or realloc. Okay? You don't own these copies of the pointers, but you know that they're car stars, and you're just telling the stack to actually dispose of those things for you, because even though the stack isn't empty, you don't need the stack anymore. That's why it's imperative that these things really be there. Okay? If you're storing a stack of ints or a stack of longs or a stack of even struct fractions where there's no pointers inside, you would just pass in null there instead, and that would be special cased away right there. Okay? Does that make sense to people? Okay. If I'm storing ints or longs or even struct fractions, which when we dealt with struct fractions just had two direct ints inside, if there's no dynamic memory allocation involved in the things I'm storing, even if they're structs, I would pass in null. The constant right here is a sentinel, meaning there's no free function needs. Okay? And it's special cased and would be observed to be null right here and circumvent this for loop. Okay? Just to make sure, I just like to ask some questions. Some of them are easy, but I want to make sure you believe the answers. Do you understand why I for loop up to log length and not alloc length, right? I have no business asking the stack to free things beyond the boundary between what's in use and what's not in use. Okay, I have no reason to trust that anything meaningful is in that extra space. Okay, in fact, I know it isn't. How come I don't free the element using this function right here just before stack pop exits? Do you understand what I mean? Like if the stack is saying, oh, they want an element back, I better return this. Why isn't the stack applying the free function to the top element before it returns it? Now, the way I framed it there, it kind of sounds like an idiotic question. But you're not really transferring a copy of the string back. You're transferring ownership of the original string back to the client. You're taking this pointer and using memcopy to replicate it in client-supplied space. So if you do that and they have an alias to a pointer that you have an alias for, and then you apply the free function to it, you're killing the string one instruction after you actually give it back to the client. Okay? Does that make sense? Okay, that's great. Even if all the code makes sense, just be sensitive to the fact that the compiler does not help you out as much as we'd like. So you really have to be very thoughtful about the placement of the ampersands and the double asterisk versus the single asterisk, and whether or not you have to dereference a car star star cast as opposed to not dereferencing a plain car star cast. Okay, the number of hops really matters, okay, and you always want to interpret the void stars to be the types of addresses you really know them to be. Okay, because if you don't, the compiler is going to just let you do whatever you want to do. And well, I mean, in theory, at compile time, you can get away with a lot, but at runtime, you never get away with anything. Okay? Does it make sense to people? Yeah?
So, the free function will understand it's not just one character we're looking at, it's a whole string. And all of it.
Well, that's not so much, that has nothing to do with strings as so much as it has to do with malloc and free. But the addresses that reside in this space right here, they were created using this function called stirdup. I think the code's still up on the board right there. And stirdup actually relies on malloc to allocate the memory. Behind the scenes, even though it's not exposed to us, it actually keeps track of exactly how much memory is part of that blob. So as long as you pass the leading address to it, it goes to a file where everything is kept track of, and it compares that address to something in a symbol table or something else to recover the actual allocation size, so it knows exactly how much to donate back to the heap. Does that make sense? Okay. And the question way in the back.
In the first line of int main, should that be a double const?
It absolutely should be. Thank you. This should either be a double star. I meant to do this. Sorry, that's the way it is always in my sample code. I just forgot to do it here. Sorry about that. There's another question that flew up over here. Yeah.
In the out part, when you call free function, I mean, for free function you did not malloc.
But I did actually. There's a malloc that happens as part of that stirdup. So every single string either has to be freed by the stack itself as part of stack dispose, or if it comes back to me because I've asked for it via stack pop, then after I'm done with it, I have to properly dispose of it. So there has to be a one-to-one correspondence between every call to stirdup and every call to free. In an ideal world where you only dispose of empty stacks, all the free calls would come in the client side. But if you ever dispose of a stack that still holds onto its elements or holding onto a subset of the elements, then the number of free calls is going to be distributed between the stack and the client. Does that make sense? Okay, that's good. Okay, so what assignment 3 is all about, it actually turns out that assignment 3 used to be a very, very difficult assignment, but I started doing this in lecture about, like, I don't know, like 3.5 years ago. And then all of a sudden things became much more clear when it come assignment time, because the implementation you write for the first half of assignment 3 is really just an extension of this. Rather than actually just dealing with push and pop as operations, those are the dynamic operations where mem copying goes on. I want you to generalize it so that you can insert anywhere. And you're familiar with that from a data structure standpoint using the capital V vector from 106 or the lowercase v vector from the STL that you use in assignment 1 and 2. Okay, does that make sense? There are two things that I just want to mention before I formally put this material to bed. And I want to talk a little bit about the implementation of malloc and free and realloc and how they work. It's actually very interesting, I think. But I have to talk about two other functions that come up during the implementation of assignment 3. I should just talk about them. Let's, this is okay. I want to write a function that's very similar to swap. I want to write a function called rotate. This actually imitates a function that's provided as part of the STL library, but I'm going to write it in pure C. And I'm going to pass in 3 void stars. Void star, I'll call it front. Void star, I'll call it middle. And void star, I'll call it end. And what I want to do, I'll use this board to draw a picture, is I want front, middle, and end to actually be sorted pointers that point to various boundaries inside an entire array. So let's assume I have an array of 50 integers. Okay? And for whatever reason, I want to move the front 4 all the way to the back. Okay? Does that make sense to people? So think of it as like a bookshelf with 50 books on it, and for whatever reason the front 4 are out of alphabetical order, and you decided to take them out as a chunk and move them to the back, but in the process you have to slide 46 books forward. Okay? Now drop the word book and use the word int, and that's what I want to do. The intent of this rotate function is if it's given the absolute opening address of the entire figure, it's given the midpoint that separates front from back, even though they're not equal sized. And then end is actually a past the end iterator in the C++ sense, but it's really the address of the first byte that has nothing to do with the array. I can manually compute the number of bytes that's right there. I can manually compute the number of bytes that's right there from these 3 void stars. Okay, this is an implementation, needs to know nothing at all about the fact that that happens to be 50 ints over on that drawing. It could have been 200 characters, or it could have been 100 shorts, and it still should do the byte rotation in exactly the same way. Okay? The slight complication here that did not come up in the swap implementation is that this right here has to be written to temporary space. You're familiar with that idea from the swap implementation. Then this right here has to be mem-copied, although that won't be the function we'll use. We'll see in a second why. This has to be mem-copied from right here to right here. Does that make sense? Okay. The problem with that is that unlike all of the other examples we've dealt with, the source region, this space, and this space right there actually overlap or can potentially overlap. Does that make sense to people? The implementation of mem-copy is brute force. It carries things 4 bytes at a time, and then at the end does whatever mod tricks it needs to copy off an odd number of bytes. But it assumes they're not overlapping. Okay? When they're overlapping, that brute force approach might not work. Suppose I want to copy these first 5 characters, and this is meaningless, and this is meaningless. What memcopy would do if I wanted to copy these 5 characters to right there, memcopy is actually quite careless, and it doesn't do exactly this, but it does more or less this, where it would actually copy the A right there, and then copy the B right there, and then copy the C right there, and then copy the D right there, and copy the E right there, except that you've trounced on the C, D, and E before you had a chance to copy it. Does that make sense to people? Now, memcopy could figure it out. It could actually check the the target address and the source address, and it could copy either from the front to the back or the back to the front, whichever direction is needed to ensure that it doesn't actually trounce over data before it's copied. Memcopy said, I don't want to bother with that. I want to run as quickly as possible, and I want the client to take responsibility of only calling memcopy when, in fact, he or she knows that there's no overlap. If they don't know if there's going to be overlap, they have to use a version of the function that's slightly less efficient, but does the error checking for them. Does that make sense? Has the same exact prototype, that shouldn't surprise you, but it's not called memcopy, it's called memmove. And I don't know why they use move as opposed to copy. Probably because it's supposed to imply that it's actually shifting somewhere in, if you're dealing with overlapping ranges, that you're really just moving bytes in a direction just by a little amount, as opposed to really relocating them, okay? So the implementation of this has to be sensitive to that. What I want to do is I want to compute a few values. I want to do int front size is equal to car star middle minus car star front. Now, you look at that, and that looks a little weird. I'm subtracting one void star from another. For the same reasons C does not allow a pointer addition, it doesn't allow pointer subtraction either. Pointer subtraction you didn't deal with too much in 106B or 106X, but it is a defined legal operation. What it's supposed to do when you subtract one pointer from another, you may think that it returns the number of bytes that sits in between them. That's not true. If they're strongly typed to be int stars, for instance, if you do pointer subtraction between 2 int stars, it's supposed to return the number of ints that fit in between the 2 addresses. And that's consistent with the way that pointer addition works. Okay? Does that make sense to people? So what I'm doing here is it's the same hack. I'm casting both of these things to be car stars so that pointer subtraction becomes regular subtraction, and I'm given the physical number of bytes that reside between that and that right there. Does that make sense? Okay. I want to do the same thing with end and middle. So at least I know how big the 2 regions are. What I can do now is I can declare a raw buffer, just like I did with the generic swap function, car buffer, and I can allocate it to be of size front size. Again, this isn't ANSI standard, but it works on our compiler, and it's so much nicer that I'm just going to do it. So now I have a character buffer that's just as big as this thing is here in terms of bytes. So maybe that's set aside right here. Because I said those were ints, if I draw even close to scale, it will be of size 16 right there. And then I use memcopy. I actually prefer to use memcopy, and I want you to use memcopy if you know you have the option to. I want to memcopy into this buffer from front size. So that if this as a figure happens to reside there, it's replicated right there. And if these are 4 ints, then this will eventually be able to stand in as 4 ints when it's placed in integer space. Then I want to take this and I want to slide it down. When you call memcopy, your heart's in the right place, but you're dealing with 2 overlapping figures. So you want to call not memcopy, but memmove with the same signature. Okay, that would be this. Memmove. I want to copy to front from middle, and I want to copy back size. Okay? Does that make sense to people? Now, if mid is very close to the end, if it's beyond the 50% point, then it turns out that mem move didn't bias very much because there's no overlapping figure between, so there's no overlapping between the source region and the destination region. But you can't, in a general sense, actually anticipate that. Okay? You could actually look at how much closer, whether or not middle is closer to front or end, and then call one of two versions that only called mem copy. But then all you're doing is the error checking that mem move would do for you. So I'd rather just deal with one implementation. Okay? Make sense? Okay. The only complexity of the last line is getting this right here into the last front size bytes. I don't actually have a target pointer for this, but what I'll do is I'll mem copy. That's okay, because I'm copying from the buffer. I'll do car star end minus front size. If from here to here is front size, then from there to there is front size. I want to copy from the buffer, and the size of the buffer is front size. Okay? Does that make sense? So you only call mem move if you have to, okay? Because you know that there's a very reasonable chance that the two source region and the destination region will be overlapping. But I want you to call memcopy if you know you're able to, because it's more efficient. And when you're starting to write systems code like this, you actually do have to think a little bit more about efficiency than you did in 106B. People argue, well, why don't I just call memmove all the time, because then I could just forget. You're right, you could, but I'd rather you not. So I actually want to pretend that memmove actually blows the computer up if the two regions don't overlap, okay? Because I want you to call memcopy if you know you can, okay? Does that make sense to people? Okay. The only other function I have to mention briefly, and actually I have plenty of time to do it, so but I just want to go over the prototype of the generic quicksort function that exists in the C language, okay? When you're sorting, there's no key. There's just the array, the element size, the number of elements, and then the comparison function is still relevant. You know how bsort takes 5 arguments? Well, qsort only takes 4. It punts on the key. Everything internally is a key compared to everything else, and it just uses the comparison function to guide it in doing all these generic swaps behind the scenes. I do want you to use qsort. I just want to put the implementation up on the board so that I can say I formally covered it. But you're all familiar with just sorting in general. Quicksort happens to be a very fast sorting algorithm. It has this as a prototype. Qsort takes a void star called base. It takes an int called n, or size actually. An int called a lem size. And then it takes a comparison function that knows how to compare two generic addresses. And there's that. And that's the prototype for it. If you want more detail, this is even relevant to some degree in assignment 2. If you happen to be stuck on using bsearch and you just want to use some more details, you can, at the command prompt, type in man qsort, and you will get more information about qsort than you care to get. But it nonetheless, at the top, will remind you what the prototype is and what all the arguments are named, so you know which ints correspond to which. Okay? You can do man on bsearch. Man is short for manual, so it just basically gives you a textual documentation of that function. Also memcopy, memmove, and I think there's some other ones. Malloc, realloc, free. These are the types of functions that are exercised aggressively by assignment 3. So you'll definitely want some resource to go to if it's 5 a.m. and you're working on it and there's nobody around. Okay. Does that sit well with everybody? Okay. So you have plenty of time to do assignment 3. It has turned out to be, I won't say it's easy by any stretch of the imagination because there's no advantage to me saying that. But it is actually a little bit less work than assignment 2, and people always start in it with a lot of enthusiasm because they think there's a lot of work to be done, and there actually is, but there's a clear list, a to-do list of things. There's like 13 functions that have to be implemented, and I provide all kinds of unit tests to exercise all of these things, okay? And you will just make very piecemeal progress on a nightly basis, okay? So that you can get it done in 1 or 2 nights if you actually know what's going on, okay? So just give yourself a little bit of a buffer in case you have some gotchas that come up while you're implementing, but it usually surprises people that it's not as much coding as assignment 2 is, okay? What I want to do now is I have 10 minutes. I just want to give you a little preamble to the more involved lecture I'm going to give on Friday about the implementation of malloc and realloc in free. Let me draw what, for the first time of many, is going to be my generic drawing of all of memory. Here's RAM. And since we're dealing with an architecture where longs and pointers are 4 bytes, that means that pointers can distinguish between 2 to the 32nd different addresses. That means that the lowest address in memory is 0, which is that null that you're starting to fear a little bit. And then the highest address is 2 to the 32nd minus 1. Okay? Whenever you call functions and the function call forces the allocation of lots of local variables, those local variables, or I'm sorry, the memory for those local variables is drawn from a subset of all RAM called the stack. And I'm going to draw that up here. I drew it a little bit bigger than I needed to, but here it is. The stack segment is what this thing is called. It doesn't necessarily use all of the stack, but for reasons that'll become clear, and there's even a little bit of intuition, I think, as to why it might be called a stack. When you call main, you get all of its local variables, and they're alive, and they're active. Okay? When main calls a helper function, it's not like main's variables go away. They're just temporarily disabled, and you don't have access to them, at least not via the normal variable names, right? So main calls helper, which calls helper helper, which calls helper helper helper, and you have all of these variables that are active, that are allocated, but only the ones in the bottommost function are actually alive and accessible via their variable names. When helper 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 returns, you return back to the locale where helper helper has local variables, and you can access those. Okay, so basically, when a function calls another function, the first function's variables are suspended, okay, until whatever happens in response to that function call actually ends. Okay, and it may itself call several helper functions and just go through lots of a big code tree of function calls before it actually returns a value or not. Okay, what happens is that initially that much space is set aside from the stack segment to just hold the main's variables, whatever main's local variables are. And when main calls something, this threshold is lowered to there to just make sure that not only is there space for main's variable set aside, but also for the helper functions variables. Okay. And it goes down and up, down and up, down and up. Every time it goes down, it's because some function was called. And every time it goes up, it's because some function returned. Okay, and the same argument can be made for methods in C++. It's called a stack because the most recently called function is the one that is invited to return before any other ones, unless it calls some other function. Okay, that's why it's called a stack. We'll get to this. We'll probably spend 2 or 3 lectures talking about not only how this thing is formatted and how variables are laid out, but also how assembly code actually manipulates the information in here. And assembly code even actually decrements and increments this boundary for us in response to function call and return. What I want to focus on is this other block of memory called the heap segment. The fact that the heap and the stack are data structures from cs106b is actually irrelevant here, mostly irrelevant. Okay? Heap in this world doesn't mean like a priority queue backing data structure. It really means blob of arbitrary bytes that this is the lowest address, this is the highest address of the heap segment. As opposed to this segment right here, which is completely managed by the hardware, by the assembly code, which actually happens to be down here. Okay, this right here, this boundary, that address, and that address is admitted to software that implements what we call the heap manager. Okay, and the heap manager is software, it's code. The implementation for malloc, realloc, and free are all written in the same file, and they basically manage this memory right here. Okay, so every time you call malloc of 40, it goes and virtually finds a block of size 40 in this and seemingly returns the lead address of it. Okay, if you haven't freed 40 yet and you go and allocate space or malloc a request for 80, it might draw it from here. It's a little bit more organized than this. It doesn't draw it from a random location, but malloc would return that. If you realloc this pointer right here, and you ask for it not to be 40 anymore, but to be 100, because of the way it's drawn, it actually might just extend this to be of length 100 and not touch the bytes that are up front. If you reallocate this and you ask for 8,000 bytes, and it doesn't happen to have 8,000 minus 80 bytes between that boundary and that boundary, okay, it might go and allocate a blob that's 8,000 bytes, copy this over, and copy it, and then free this right here. Okay, so this really is a sandbox of bytes, and whether they're integer arrays or char star arrays or struct fraction arrays, it's all immaterial to malloc, because it only allocates things in terms of num bytes requests. Okay, does that sit well with everybody? Okay, so what I want to do is I want to be a little bit more organized in the way I demonstrate how malloc and realloc and free work, because it isn't that rain pell mell about allocating bytes. It does have some normative process that's followed behind the scenes, so it can be as efficient as possible on your behalf. Malloc and free and realloc are actually called enough, either directly or via things like operator new and operator delete, or stirdup, or your constructors or whatever, that it wants to make them run as quickly as possible. So what I'm going to do is I'm going to explode this picture to this board over here. Actually, this one's better. But I'm going to emphasize the fact that it is one big linear array of bytes. And so rather than drawing it as a tall rectangle, I'm going to draw it as a very wide rectangle and make it clear that this address right there is that one right there, and this address right there is that right there. Okay, does that make sense to people? So I go ahead and I declare void star A is equal to malloc of 40. This isn't exactly what happens, but it's pretty close. It will usually search from the beginning of the heap and look for the the first free block of memory that's able to accommodate this size request. And initially, since the entire heap is available, what will happen is it'll do whatever accounting behind the scenes is necessary to clip off the first 40 bytes, record that it's in use somehow. We'll talk about that in more detail on Friday, and return the address of that right there. Does that make sense? Okay. Next line does this, malloc of 60. It will take this, at least this naive approach, and that's what it does very often. It's just scan from the beginning of the heap and find the first open block that's able to meet this request. It sees that that's in use. It's able to quickly hop here. We'll see why on Friday. And say, okay, this entire thing is free. That's certainly bigger than 60. So I will do that and then return that address. Okay? Punting on realloc for a second. If I go ahead and call free on A, it will go in, because this address, this arrow right there, the tail of it is held in the A variable. It will go and remove the halo around this memory. It doesn't clear out the bit patterns, because the bit patterns are supposed to stop mattering, and then donates it back. So that if I do this, void star C is equal to malloc, and I'm obnoxious about it, and I say 44, it will look at this block right here. It will record it and note that it's a 40-byte free block that could have been used had this number been less than or equal to 40. But since it isn't, it has to hop over and consider this right here. So it will clip this off and return that address and bind it to C. If on the very next line, I do this, some implementations actually carry off where the last search ended, but the way I'm talking about it, it always searches from the beginning, okay? This time, this block is big enough to meet that size request, so it might clip this off, record that it's 20 bytes wide, and return that pointer again, okay? Does that make sense? Entirely software managed with very little exception, okay? And I say exception because the operating system and what's called the loader has to admit to the implementation what the boundaries of the stacks of the heap segment are. But everything else is really framed in terms of this raw memory allocator, okay? As far as realloc is concerned, if I pass this address to realloc and I ask it to become bigger, it'll have to do a reallocation request and put it somewhere else, probably right there, the way we've been talking about it. If I didn't ask for that to be realloced, but I asked for this to be realloced, to go to 88, it would just extend it in place. What's going to happen, and we'll be more detailed about this come Friday, is that there really is a little bit of a data structure that overlays the entire heap segment. Okay, it is manually managed using lots of void star business. In a nutshell, let me actually, in the final 10 seconds here, let's say that this is the heap again. And just to emphasize what's been allocated and what hasn't been, let's say that this has been set aside. Let's say that this has been set aside. And let's say that this has been set aside. The data structure that's more or less used by the heap manager overlays a linked list of what are called free nodes. Okay? And it always keeps the address of the very first free node. And because you're not using this as a client, the heap manager uses it as a variably sized node that right in the first 8 or 4 bytes keeps track of how big that node is. Does that make sense to people? So it might have, subdivide that, and to the left of that line might have the size of the node, and to the right of that line might actually have a pointer to that right there. Okay? Now it's not like there's ints and doubles typing any of the material over here. The heap manager has to do this very generically. So it constantly is casting addresses to be void stars and void star stars, okay, in order to actually jump through what this thing called the free list behind the scenes to figure out which node best accommodates the next malloc request, okay? When you free this node right here, it has to be threaded back into the free list, okay? Does that make sense? I'll be a little bit more detailed come Friday as opposed to this hand-wavy after 11:50 comment, okay? But I want you to understand all this, okay? We'll see you on Friday.